Hello students, the continuation of thermodynamics. In that we are going to learn about the analytical method for the work done of the expansion and the non-cyclic process, the cyclic process and the first law of thermodynamics. Yes students? Yes students. Now the analytical method for the work done during the expansion. See the diagram students, that you can consider there a gas contained in a cylinder of cross-sectional area A and which is provided with a frictionless movable piston. See, there is a frictionless movable piston which is joined with the container, and you can take P be the pressure of the gas. If suppose P be the pressure of the gas, then force which is exerted by the gas on the piston that we can say that F which is equal to PA. F force which is equal to P into A. Right. Now, we can take that the gas, suppose expands a little and it pushes out the piston through a small distance dx. Then we have to take the small work done by the gas, that is dW, which is equal to F into dx. So that is equal to F here, we can say that PA into dx. So dW which is equal to P into dV, because A into dx which is equal to dV here, right? So because of the distance with the area, that is the volume, you can consider it. So that dW, the small distance, the small work done, which is equal to P into dV. Got it? So that is change in the volume of gas. So we can say this is change in the volume of gas. Right. Now, you need to know about the total work done by the gas. When it is suppose the volume which is increases. So, the total work when the volume increases. So that means from V1 to V2 we can take it. Then the W which is equal to integration. For you need the total work done, you have to integrate it. The integration of dW which is equal to V1 to V2 P into dV. Got it children? Yes. Yeah, now let us see about non-cyclic process and the indicator diagram method for the work done during the expansion. See, what is non-cyclic process? We can say that the system does not return to its initial state. That means, if suppose a non-cyclic process is one which the system, we have taken any system, this will not come to the initial state. Now, we'll show through the indicator diagram of work done during the expansion. See the graph students. See the points, you may observe that A and B, that is represent the initial state of P1 and V1, that is for the pressure 1 and the volume 1, right? So the final state we have given as P2 V2. Observe the graph children, the nature of the graph which is going down, and P1 V1 let us take, we have taken as the volume 1 and the pressure 1, and we have taken that as P2 V2 as the final state in the system, that we can consider this as a PV diagram, right? So this in this PV diagram we have taken, and at any point A, see that we have indicated the particular part. At any point A, let P and V be the pressure and the volume which getting increases. Suppose it is getting increases from V to V plus dV. Then what will happen? Here the pressure will remains constant. Right? See the particular part of A, B and C, D. See that? See, here we can take that AD which is equal to BC. That is equal to what? P, that pressure. And here the CD which is equal to dV. That is the change in the volume it's happening. So that the work done dW which is equal to P into dV. That means what? What we have taken here the P, AD into this CD. Right? So the W for the whole work done, we can say by observing the graph, the area of A, B, C, D, A. Right? See the nature? So we can take the work done which is equal to area of A, B, C, D, A. So as we know that from the analytical of we analyzed already about the work done during the expansion. From that we can conclude the indicator diagram of PV, that is W which is equal to what? The integration of V1 to V2 into PdV. Got it, children? So from this you may know about the area which is enclosed between the PV diagram and the volume axis. Right? So the next one is cyclic process. See, cyclic process which means the system will get returns to its initial state. Right? So after it undergoes a series of changes if occur, also the system will returns to the initial state of it. Right? Now we'll see about the work done during the cyclic process. During cyclic. Right. See, observe the diagram, children. Now, if suppose you have taken the gas, first it expands from the state A to B, then along the path of AXB, and then it undergoes the compression to return to the state A along the path BYA. Check it, children. First, it expands through the path AXB. Then the second process, that is, it is undergoing to the compression. So it returned to A along the path BYA. Now the work done during the expansion, the first state we have taken for the expansion. Now the work done W which is equal to plus, see the look at the diagram, that we can take the area which is of AX and BC DA. Okay. The next one is for during the compression. So during the compression, it is coming written so that you can take it as negative area of BY ADC, that B. Observe the path of the diagram, children. So this is for the expansion, it is moving in the positive. Then it is written to that we have taken that negative area of BYADCB. Now you need to know about the total work done. So that this W which is equal to W1 plus W2. So that is equal to AX BCDA minus BYADCB. Then that W value which is equal to plus area of AX BYA. See, this is the total work done value which is for that is AX BY A. Now we can conclude the cyclic process actually, that is the work done per cycle is numerically we can say that is equal to the area of the loop. So this is equal to the area, right? And we can say that the work done for, if suppose you are tracing the loop in the clockwise direction, the work done is clockwise means WD, which is equal to what? It is positive. Okay. If suppose that is anti-clockwise, then this work done nature is negative. Right, students? Yes. First law of thermodynamics. It is simply the law of conservation of energy which is applied to the system, right? In which the energy is transferred from all the surroundings is taken into the consideration. Now, according to the first law, the heat which is supplied to a system which is capable of doing work, then the quantity of heat which is absorbed by the system will be equal to the sum of the increase in its internal energy and the external work done of the surroundings. So this is the statement we can prove through the example, right? See the diagram, children, and we have taken the absorption of heat by a gas in a cylinder. It is attached with a movable piston. Here, that we have taken del Q, which is the heat supplied to the system by the surroundings, and the del W, which is the work done by the system on the surroundings, and the del U, which is nothing but the change in the internal energy we have taken. According to first law of thermodynamics, the statement which says that the heat which is supplied to a system, it is capable of doing work, the quantity of heat which is absorbed by the system is equal to the sum of increase in its internal energy and the external work done. That means what? Del Q, which is equal to del V plus del W. So this is the statement, the meaning of the statement which is given as the mathematical relation, right? Now, here the system which I have showed is the gas which is containing in a cylinder, and we said it is provided with the movable piston. So it is a movable piston which you are seeing, right? Then the gas does not work in moving the piston. Now the work done by the system which is against the constant pressure P, del W, that is the change in work, which is equal to F into D. Right, the work done, force into displacement, F into D. So this is PA into dx. So that is equal to what? P into del V, right? So this is P into del V we have given, that we can say as per from the first law of thermodynamics, here del Q which is equal to del V plus, instead of that del W, you can write P into del V. Got it? So this is the first law of thermodynamics. Yes, students, so far we have learnt about analytical method for the work done of an expansion and cyclic process, non-cyclic process, and the first law of thermodynamics. Thank you, students.